1.4 Algebraic limits. You're going to have to determine limits algebraically, and there are a lot of methods to help you accomplish that. But one thing that you should always try first, always, is direct substitution. Now, if you get 0 over 0 or infinity over infinity, we got to change it so that we don't get that anymore. So, but you should always try it first. Notice I have that unit circle stuff up here. Might need it soon. So the limit has cosecant of x versus direct substitution. You should be able to figure that out. Right? And so remember that's a reciprocal sign. And so we would get this negative as a third quadrant. So we have negative 2 over square root of 3. Okay, if you can't do that right away, you need to practice it. Okay, now when you plug in square root of negative 4, I know it says from the left, but just try to plug it in. Square root of 4, okay, we get 2. Beautiful, so always try that first, every single time. Now, if you know that there's a vertical asymptote, that's going to help you solve the limit faster. Okay, so if we plug in 1, okay, 1 over 1, that's, or 1 plus 1 is 2, 1 minus 1 is 0. That's not 0 over 0. Okay, so we don't have to eliminate any that, that's not very correct. We would know there's an answer for that variable. So, sorry, 0. It can't approach anything. All right, same thing over here. If we plug in pi on the top, we get pi. If we plug in pi on the bottom, however, we get 0. So we have a number of 0, so it does not exist. Okay, limits at infinity. We practiced that in the last section. These ones are easy to spot because there's an infinity sign. Check the degree or the growth rate of the numerator and the denominator. Okay, and the next one, ln of x. You know, ln of x normally looks like this. Okay, but ln of absolute value of x. That means that if you want to plug in -1, you're going to take the value at 1. Okay, if you want to plug in -2, you take the value at 2. So it's going to look something like this. So as we approach negative infinity, in this case we approach infinity. Piecewise functions, you just have to take it by piece. Okay, so in this case, x approaches 2. So we'll do the left side. The limit as x approaches 2 from the left. That's 1. Limit as x approaches 2 from the right. 1 plus 1 is 2. All right, so they're not the same. The left hand limit doesn't equal the right hand limit, so the limit doesn't exist. Okay, and then we have part B. Same kind of problem. Take the limit as x approaches pi from the left or the right. Actually, in this case, it's going to be the same because anywhere it's not pi, we're using this top function. So sine of x, plug in pi, get 0. Okay, at pi, it's 1. That doesn't matter. That means everywhere the graph is 0, and then there's a hole. It jumps up to 1, and then it continues again. Remember, limits don't care specifically what's happening at that case, just what it looks like is happening. So it looks like it's approaching 0. Okay, the squeeze theorem. This one was pretty easy to recognize. Okay. Here we have find the limit as doing it as x approaches 1. Well, we just take both sides. What's the limit as x approaches 1 of ln of x plus x squared? So 0 plus 1 is 1. What's the limit as x approaches 1 of e to the x minus 1? 1 minus 1 is 0, e to the square is 1. And remember, we learned how to write that out. So since this happens ln x plus x squared is less than or equal to j of x is less than or equal to e x minus 1. Then the limit as x approaches 1 of j of x equals 1 by the squeeze theorem, or the sandwich, if you want to call it sandwich theorem. Usually makes me hungry though, so I stick to squeeze. All right, now if we get 0 over 0 or infinity over infinity, we have to use some other things. One method that we can use is to divide out, and this works really well if you know how to divide polynomial functions. Okay, so you plug in 2 in the top, you get 0. You plug in 2 on the bottom, you get 0. So you know that for something, there's a hole there. So let's see if we factor this. We get x plus 2, x minus 2 over x minus 2. Cancel those out. Because we don't care for a limit exactly what's happening in 2. We just want to look around it. Have a look at it. 2 plus 2, 4. Done. All right, this case, maybe you don't know how to factor this. So this is where synthetic division comes in. But if you plug in 1 in the top, 1 in the bottom, you get 0 over 0. Okay, so if we have x minus 1, that 0 is 1. Okay, x cubed, we have one of those, 0, x squared, 0, x, and negative 1 is our constant. Go ahead and divide that. 1 times 1. Okay, so what that says is one. So we cross these out, plug in 1, 3. Okay, now in this last case here, if you plug in negative 1 on the top, negative 1 on the bottom, you're going to see that you get 0 over 0. So that means that both of these polynomials are divisible by x plus 1. So you have to divide those, okay? So let's see, one way we could do it would be synthetic division. So with the top function, come on. So we have 1, negative 1, negative 1, negative 3, negative 4. Great, so we do all of this. Good, we got a 0. Okay, so then we can factor the bottom also. Let's see, negative 1, 2. Well, you should be able to do that anyway. That's actually a lot easier to just do it this way. Look, 2x, whatever, minus 3, x plus 1. Okay, that was easy. Now this one ends up being x cubed minus 2x plus 2x squared plus x minus 4. So let me rewrite that here. After we cancel out this term, the x plus 1 term, so we have in the numerator x cubed minus 2x squared plus x minus 4 over 2x minus 3. Okay, now let's see if we can plug it in. Remember, always try direct substitution first. And it looks like in this case we can. I think we get negative 8 on the numerator, negative 5 in the denominator, so we get 8 fifths. So not so bad. You might need to brush up on your synthetic division, but it's still not that difficult. Okay, and this one takes a little bit more space when we do this. So RATCON, rationalization conjugation. You have to know what the conjugate is. So again, always try direct substitution. We get 1 minus 1, 0 over 0. Now we have a problem. We can't just cross out x's. So what we do instead is multiply by the conjugate. Square root of x plus 1 plus 1. We can't just do it off the top, okay? Because we have to multiply by that clever form of 1. Okay, so like, I try to save a little bit of space by multiplying it out. So we get x plus 1 minus 1. At the bottom, I'm going to leave it alone. At the top, I get x. At the bottom, I get x times this quantity. They cancel out. How convenient is that? So we get 1 over square root of this. There's 0 now. We get 1 over 2. Okay, that one's not too bad. So then I would like you to try this one. And write your answer in the whisk. And then so it's going to be easier if you multiply the top and the bottom by the conjugate of the denominator. Okay, so you try that, write your answer in your whisk.